Any questions?
To be,
Or not to be?
hollow cube side length of 4 meters or its electric flux. If there's a 14 millicoulomb charge halfway between the center of the cube and one of the corners.
Right?
I'm assuming it's the same, but I'm not 100%.
The Gauss's law tells that if I take the electric flux through any closed surface, the circle being closed surface, that's going to be equal to the enclosed charge over epsilon sub 9. So it's the cube. The cube is the surface, and no matter where that charge is inside it, it's still the charge enclosed. Is that sufficient?
Yes.
Okay.
Yeah.
Yeah, it was once you recognize that it's a Gauss's law problem, then potentially it's relatively easy. If you actually had, I'm definitely not asking you to calculate it this way, because that would be incredibly difficult. So you either see the trick, or I guess you see the trick, or you think, no, surely there's no way that he wants us to do that interval. Or you have tortured yourself. If that's what you're into, hey, I'm not judging. Other questions? All right, let's talk about capacitors then. Parallel plate capacitors. So I take two parallel plates here. I know that if the distance between them is small compared to the dimensions of the plate. So for example, if you had 10 centimeter by 10 centimeter metal plates, and you had a dielectric that was 0.1 millimeters in between them, the distance between them is definitely tiny relative to the dimensions. Let's assume it's a D by D plate, capital D. So if D is much less than big D, infinite plate approximation is valid. If you are beyond the 10 center, or roughly much less than, typically if you need a number, if D is less than 10% of, if little d is less than 10% of big D. If you exceed it, it's still not a bad approximation, but you're getting more and more off the front of the plates gets better apart. The symbol for a capacitor is just that. So if I had a circuit diagram, I think some of this is a repeat, and that's a sad marker. And batteries, we've done symbols for batteries yet? I'm mixing up the classes.
It's the one big one and one small one.
Yeah. So this would be a DC power supply connected to a capacitor. Similar to, I guess, sort of what you did in lab last Friday. You have multiple ones. So I'm going to assume that they were really close to each other. I'm going to use the infinite plate approximation. So I've got my two plates here. I have an electric field in between of sigma over epsilon naught would be the magnitude of the electric field. That would be my positive plate and negative plate. I know this is my positive plate because it's connected to the positive side of the battery, positive terminal, and negative is connected to the negative side. When I actually make the connection, I'll have electrons start moving. The electron's gonna be moving this way, cruising up. An electron will get on one plate, it will chase an electron off the other plate, and will slowly work its way there. I saw one calculation, which I think gives a reasonable ballpark figure, is the speed at which the electrons move along the wire is a couple centimeters a second. So what's really happening is that when I set up the circuit, this electron that comes out of here, well, one, it's gonna set up on the plate, but even if I connected that, this battery's gonna take some amount of time to get all the way over here, but we don't have to wait that long for actually have a current flow, it comes on immediately. And that's because all we need is for charges to move. So what's happening is that once I make the connection, I'm gonna have a hole here, an electron's gonna fill it, moving the hole this way, and then an electron will fill that, moving it that way, and you'll have a hole moving in this direction. I have seen lectures in which they talk about, instead of an electron flow going this way, they will talk about holes moving in the opposite direction. As a matter of fact, the direction of the hole movement is the direction of current. Current represented by a capital I. I can't remember what I did last Friday, so this could very well be repeats. All right, so current is flowing onto here. In other words, we have electrons flowing in the opposite direction. Some textbooks will call this electron current and traditional current. I call this current. The electrons happen to be going the other way. Electrons are the things that are really moving, unless you want to consider the movement of the whole.
Is there electromagnetic waves too?
If, not necessarily, if you have the electron moving, you are creating a magnetic field. The electron itself has its own electric field. The way that you would get electromagnetic waves is to have either the electric field or the magnetic field start to vary. In a nice ideal situation where the current just flows, you're not having, it's not oscillating back and forth, then you would not have an electromagnetic wave.
I read something somewhere at one point where it was like there's charge that travels on the outside of the wire, and then there's like electrons that travel through the wire too. Like maybe it varies at different times. I don't know.
I mean, it's quite, so reality is, as the electron flows, it doesn't really flow in a straight line, it tends to drift in a particular direction. But I assume you're not talking about coaxial cable.
I don't know.
Coaxial cable, you'll have, basically current flowing in one direction through the middle and in the other direction on the outside.
Yeah, maybe.
In terms of the mechanics, if we're looking at a cross-section of a wire, the electron is going to be, as it moves in a particular direction, will be sort of bouncing around. Okay. Kirchhoff. Did I mention Kirchhoff on Friday?
No.
I think it's 2 H's. I don't know. It just doesn't stick. I always get to this point because 2 H's doesn't look right, but I think there are 2 H's. Kirchhoff, he came up with two rules. One is called the voltage rule or the loop rule. The other one's called the current rule or the junction rule. So the Kirchhoff's rules. There's the voltage slash loop and the current slash junction. The current rule, or the junction rule, is that if I have any junction, any place where current can split, whatever current I have flowing into it, I have current, the same amount of current flowing out. So this is just at any junction, actually at any point, current in equals current in equals current out. We're primarily concerned at junctions. You might start thinking of exceptions, and we'll address at least one of them. Now, let me actually bring up an exception to that and just sort of leave that as a cliffhanger, and we will talk about it later. As I have an electron flowing onto this plate right here, I have an electron flowing off, or I have current flowing here and then flows here. So if I look at just the left plate, it looks like I have current flowing onto the plate and I don't have any current flowing off the plate because there's a gap. And so that will get resolved by Maxwell. And so we get to Ampere's rule with Maxwell's correction, and that will account for that. So that's probably in another month. The voltage rule. So if I have an electric potential here of 8 volts, and I travel around, and I end up back right there, what is the difference in potential? All right, that one hand gesture, that was correct. And I got 2, there we go. So the change in potential, no matter what, if I take that path, if I end up back where I started, the change in potential is 0. And that is the essence of Kirchhoff's rule. If I start anywhere on a circuit, and then I travel around, if I end up back where I started, the total of all my potential gains and losses is 0. So if I look at this battery hooked up to here, if this is a 12-volt battery and I'm going from the negative to the positive side, I gain 12 volts. I cruise along, I cross over my capacitor, come back, I should be at 0. So if I gain 12 volts here, I have to lose 12 volts there. Also supporting the idea that this is the positive and that's the negative side is because if I'm going this way across it, I have to lose 12 volts. In other words, the voltage across here, going from left to right, would be negative 12 volts. Going in that direction, negative 12 volts. Going in that direction, positive 12 volts. So as long as I'm hooked up to a battery, if I just have a simple circuit, just a single capacitor hooked to a battery, that voltage is set. No matter what else I do, that voltage is set by the battery. So it's something to keep in mind. So if the battery is connected, to the capacitor, the voltage of the capacitor is set. So if I take my capacitor and I move it apart or move it closer or change the size of it, change the material, whatever I do, as long as it's connected to the battery, I'm fixed. So I charge it up. I turn on I connect the circuit. I have current flowing through here. I charge them up, and eventually it gets harder and harder to put more charge onto here because, yes, it start out, it's easy. You got a big wide open space. The electron can go onto it. It's fine. But the more electrons I put onto here, the harder it is to put an electron on there because, well, I got a whole lot of electrons over here going, I'm not sure we have enough room. But they'll keep getting forced on there up to a certain point. And at that point, we are reached maximum charge. So the capacitance, the capacity for it to hold a charge seems like it would have something to do with the amount of charge it can hold based upon how much voltage I have. If I crank up the voltage, I'm cranking up the effort to push these charges out. And so we come up with a definition of a capacitance, which is the charge divided by the voltage. This C right here is capacitance. It is not coulombs. And so if I have a a set capacitance, then if I know what the voltage is, I can figure out how much charge is gonna be on the plates. And that will be there for years.
So you reach maximum capacitance and maximum charge, I guess?
The capacitance would be the maximum charge per unit voltage.
What's the point of capacitors in practical application? So it holds charge to do other things? Or
Yeah,
something?
yeah.
Okay.
Not taser or stun gun? Stun gun is the one that shoots, taser is the one that is right up close, or vice versa. That basically you get a huge capacitance there and you hit somebody and now it has a path. So in practical terms, if I have a capacitor that stores up charge, I don't know why I went to this example first, there's a less violent one. But it stores up charge, and then all of a sudden, if you have a way of connecting it, you'll get a huge charge flow through it. So if you have a taser and touch it, then you basically get a huge charge flow coming through very quickly.
And in circuits, it stores charge to move to other places or something, or do other things in the circuit?
Yeah, if whenever you need a very quick pulse of current. So under no circumstances, you don't want a surge. Surge, that's the word I was looking for. When you need a big surge of current, flash bulbs. You're taking because if you just had current flowing through it, it'd be probably a light glow to the bulb. But to get a flash, you need a lot of current very quickly, so you build it up and you store a whole bunch of current on a capacitor. You hit the button, connects the circuit, and now you get this huge surge of current flowing through, and you get a very bright light.
That's the only reason to use capacitors, is to release it all at once like that?
With any of the circuits that we're dealing with, resistors, inductors, capacitors, those are the three main ones we'll deal with, diodes, etc. It's all about controlling current and making sure you can use current when you need to. So my experience is it's just to store current so that you can get a quick pulse at the end. I guess there's a resistor in there that's just going to slow down the current. Yeah, pretty much. If you've got, flashing back to battery versus capacitor, because they both provide charges. And one stores it, battery stored as a chemical process.
That would have been my next question. Yeah.
And this stores it as just sort of raw charge.
Like mini batteries?
Yeah, there are some definite similarities between the two. I was about to say, if you needed a slower release of charge from a capacitor, you still could do it by throwing a resistor into it. So you've got this connected to some resistor, circuit's not completed, and then when you complete the circuit, there'll be a slower drain than necessary, but right now I can't think of a practical application why you would do that, but I'm sure it exists out there somewhere. Other questions? The class feels lopsided. Got all this space over here. Just dropped it again. Units. Well, I know that the units of capacitance therefore must be equal to the units of charge over the units of voltage. What are the standard units of charge?
Coulombs.
Standard unit for voltage?
Volts.
So the units of capacitance is a coulomb per volt, which is too much for people to write. It always strikes me as strange because the electric flux is still Newton meter squared per Coulomb. They haven't bothered coming up with a shorthand for that, but this they do. It is the farad. And I know that was mentioned on last Friday, or the Friday before that. What's named after? It's not farad.
Faraday?
Yep, that's the one. So if I have a 12-volt battery here, connected to a 3 microfarad capacitor, how much charge do I store? Well, it's a simple plug and chug. The charge would be equal to the capacitance times the voltage, and so I get 3 times 10 to the -6 farads times 12 volts, and I get 3.6 times 10 to the -5 coulomb. And again, we're in the situation, this C right here and this C right here do not mean the same thing. This C is capacitance, this C is coulombs. So let's just pretend, we'll use that situation right there. In this problem, these plates are 10 meters by 10 meters. Huge. Let's do something modern. What the heck, we'll still go with it. So the plate, we'll assume it is a 10 meter by 10 meter. What is the surface charge density? Or how would you find it?
Area and multiply by.
Just take the charge divided by the area. which is
Yeah.
100.
So surface charge density is gonna be the charge divided by the area. So we have a charge of 3.6 times 10 to the -5 coulombs divided by 100 square meters. And we end up with 3.6 times 10 to the -7 coulombs per square meter. What is the electric field between the plates? Or how would you find it?
You would use, could we assume it's infinite?